Well, thank you very much for that introduction, and thank you very much to the organisers for the invitation to come and talk to you today. What looks to me like a very interesting programme that you have set up, and I look forward to staying around to listen to some more of the talks and the discussions as the day goes on. But to start, I will indeed, as Andy said, talk to you a bit about gravitational waves, to a large extent where we are, what our current results are, what looks promising to us, and again with the theme of, again, where we're going, of what does the future hold, as Andy said, many of your early career researchers, so what's coming down the pipeline in the field of gravitational waves. And most recently, of course, we were delighted that the Nobel Prize in Physics in 2017 went to the field of gravitational waves, and specifically to three of my colleagues, Ray Weiss, Barry Barish, and Kip Thorne, and the part of the citations there, for decisive contributions to the LIGO detector and the observation of gravitational waves. And I think a couple of things I wanted to say about this, one of which is I think there are actually, I can think of a few things associated with the detection that made it particularly interesting. The citation says for the observation of gravitational waves and contributions to the detector, and buried in that, I think there are multiple things that make this a very interesting discovery. But underneath, both the Nobel Committee and actually notably during the lectures themselves, the laureates were very generous in recognizing that it is a collaborative project, it's an international project. As Andy said, it's no longer the lone PI having a fantastic idea. This involved over 1,000 researchers from more than 20 countries, again picked from the Nobel website there, and together that took decades to get to this point. And again, hopefully during the talk, some of the things I'll talk about will explain a little bit about why that is. But first of all, again, that discovery, again, some of you will have seen this lovely animation before, was of course from the gravitational waves from a particular source in that first detection, two black holes, stars that had run out of fuel, got to the end of their life, their cores had collapsed under the gravitational force, collapsing down into these regions of space with gravity so strong that not even light can escape, that we give the name black holes. Two of those spiraling round, distorting space-time around them, and actually causing it to oscillate, getting closer and closer together, losing energy in the form of gravitational waves as they did so, in a very characteristic way. And underneath that lovely animation, you can see a trace that's being produced in line with the animation of the gravitational wave signal that we would expect to detect here on Earth, a long way away from the event itself. And it is very characteristic in terms of how the let's just go forward and let you see that again, of how the source affects space-time and causes it to vibrate. So underneath there, you can see what that trace is actually telling us about is how distances in space-time are being stretched and squashed as gravitational waves pass by. And that's the effect that we measure here. And at the beginning of the trace there, the trace is actually telling us to a large extent about the masses of the black holes, the individual black holes. As they get closer and closer together, the evolution gives us other information about how the source is behaving. And then finally, the signal peaks as the black holes themselves merge. And then the final part of the trace tells us about the new black hole that's formed and its properties. And all of that's encoded into this vibration in space-time, into this gravitational wave signal. So it's a very different way of studying objects in the universe. It's a very different way to do astronomy, not by getting an image, despite the fact we have these beautiful colored animations, of course. For this particular event, when we looked with electromagnetic telescopes at broadly the area of the sky we believed the source to be in, and I'll talk more about that, there was no signal seen. We got no image. So it's actually the trace itself that we use to extract the properties of what produced it. And of course, for this particular signal detected, that was our lovely animation, but here's the data reported back in February 2016. It was very characteristic of a particular kind of source, two black holes colliding. And from these traces, you can see here one from the Hanford instrument, one from the Livingston instrument, from the paper produced at that time, we extract the properties of the source. We can tell that that final black hole was about the size of Iceland, that it was about 62 times the mass of our sun, and that it was spinning about 100 times a second with a point on its event horizon traveling at nearly half the speed of light. And all of that information is encoded in these wobbles in space, these wobbles in space-time. Underneath here, you'll see other plots, and this is just a different way of visualizing what we have. As I say, we don't get an image, we get this trace, but we can plot this information in different ways. And so along the bottom here, you'll see time, the time evolution of this wobbling of space. Up the side here, frequency. So there's the increasing frequency of this signal as time evolves, and the colors are telling us about the size of the signal. So we see this very characteristic sweep of the chirp of the vibrations of space-time caused by these gravitational waves. So that was our first signal, again, and I've talked about the vibrations of space. What do we physically measure, and how do we do it, and why did it take us so long? Well, it was just over 100 years ago that Einstein, with his theory of general relativity, predicted that there must be these traveling gravitational signals produced by the deformation of massive objects. But in fact, special relativity tells us there must be gravitational radiation, since it tells us that no information can be traveling faster than the speed of light. That includes gravitational information, so there must be traveling gravitational signals. But general relativity then codifies that. The equations of GR have these wave solutions emitted by a rapidly changing configuration of mass, predicted to travel at the speed of light, and I'll talk more about that have a physical effect, with that physical effect being to change the distance between inertial points in space transverse to the distance of travel. So gravitational waves then coming in through the lecture theatre here, traveling into the board, the physical effect that they would have if we picked a patch of space on the board would be to stretch it in one direction and simultaneously compress it in another direction. The physical effect that they have, but sadly exaggerated here enormously so that you could see that exaggerated for effect. And we can quantify how much we would expect this effect to be. We, of course, measure this effect, these changing distances, using laser interferometry with the Michelson interferometer, familiar from undergraduate physics labs the world over, as the basis for our instrument, more sophisticated versions of this, where we use the interferometer itself, the change in intensity at the output here, to sense changes in the arm lengths of the interferometer. So the physical effect then of the gravitational wave stretches one arm here by some amount delta L, compresses the other arm by some amount delta L. So if L is our arm length, delta L is how much one of these mirrors in the instrument has moved. We quantify that by H, the strength of the gravitational wave. How much has this moved? And H we can calculate from GR, from knowing the properties of typical sources. And if we do that, we find out the strength of a typical gravitational wave is about 10 to the minus 22. So if we decide we're going to build a 1 meter Michelson interferometer on a bench top, its mirrors will only be moved, its arms will be stretched or squashed by 10 to the minus 22 of a meter. And so that's a tiny amount. And it tells us, again, if we look at our definition of H here, we want to make L as large as possible. To make delta L, the effect, as large as possible. And so it tells us we don't want to be 1 meter instruments. We are not, this is why, these are not tabletop devices. They have to be large, again, because gravitational waves have a tidal effect. It's a strain in space. The larger we make L, the larger this effect will be, again, and that gives us a better chance of doing it. So that's why Despite the fact that we explain the effect using these stick diagrams of Michelson interferometers or so, reality goes in this direction. Things get far more complicated when you want to sense mirror displacements of less than 1,000th the size of a proton. And this, I think, is one of the other reasons why this was a sort of an achievement worthy of the Nobel Prize, was not only the detection itself and the verification of Einstein's prediction, but to some extent the enormous measurement challenge in achieving this. And that itself is one of the reasons, and Andy alluded to this in the introduction, that this is an international project. It took the combined efforts of multiple countries, although the instrument is based in the US. The two LIGO observatories are based in the US, again supported by the NSF over many decades. But it really took the contributions from multiple countries as partners in the project to be able to meet the measurement challenge. From the UK, again as partners in this, one of our contributions on the instrumentation side was around actually how we physically suspend those mirrors to be almost motionless in space, so that when a gravitational wave passes by, they are quiet enough, they are not moving to an extent that means they can be affected by the gravitational wave at a level we can measure. And to do that, we have to make sure the Brownian thermal motion of the mirrors themselves, and these are macroscopic objects, 40 kilograms of ultra-pure glass, suspended on pure glass fibers, to reduce that thermal motion. The low intrinsic dissipation of fused silica makes an excellent material for that. The instruments themselves are illuminated by a laser, 200 watts of continuous light at 1064 nanometers from a custom-built neodymium YAG laser, and that was a contribution from Germany, from our colleagues in the Albert Einstein Institute there, to design and custom build these highly stabilized, high-power, very novel lasers. And again, the third large international partner was Australia. We have these 4-kilometer long LIGO instruments that have cavities in their arms. Those cavities have to point at one another and remain pointing at one another to allow light in the arms to build up. So these are not quite simple Michelsons. They have other mirrors in the arms to make Fabry-Perot cavities. With highly reflective mirrors, that's actually a very difficult challenge to find a way to actually be able to control those cavities to point at one another, and a contribution from Australian colleagues was around the system to let that happen. So a truly international project, all going into these observatories, again, one based in Hanford, again, you saw the signal from that, one in Livingston in the US, and operated by Caltech and MIT, but all as part of the LIGO scientific collaboration. Again, more than 1,000 scientists from a number of countries around the world, all working together on this project. And LIGO itself is part of an international network of detectors, the 2 LIGO observatories in the US, but there's also the Virgo Observatory in Europe. Again, we, with our German colleagues, operate the GEO instrument in Germany and have done for many years. It's a smaller instrument, but with testing some of the advanced technologies that we talked about that then went into the LIGO instruments. And GEO's been operating for some time. LIGO, of course, turned on in 2015. Virgo in 2017, again with quite spectacular contributions already to the science. And as we'll see, coming in the next few years, we will have another instrument in Japan and a third LIGO instrument in India. And this is scientifically driven, the need for this network of detectors, and I'll talk more about that. In terms of the results then, in terms of observing and detections, the last couple of years have been unexpectedly, I think, exciting, particularly last year for us. So that first detection came in September 2015, and what you'll see here are numbers that tell us the volume of the range, the distance out into the universe that the LIGO observatories in particular, I think, would be sensitive to colliding neutron stars, the gravitational waves from neutron stars. And why is that when the first thing we detected was black holes? Well, it was unexpected. We did not expect our first discovery to be colliding black holes because the rates were pretty uncertain, in fact, really quite uncertain. Neutron star collisions, on the other hand, we thought we had a better handle on, and so we could use that as a yardstick. That was really what we expected to detect first. So our estimates of the performance of our instruments are typically in terms of how far out we'd be sensitive to colliding neutron stars. So for the first observing run that started in September, these red lines here indicate 2 black hole collisions detected. The instruments, the LIGO instruments, were then turned off. Virgo wasn't quite ready, and the LIGO instruments were worked on to commission, because when we made those first detections, they were not, and are still not yet, at design sensitivity. That was expected. These are large, complicated instruments, and so it takes time to work and understand all the noise sources to get them to design sensitivity. So there was a period of time with the detectors off, and then the second observing run started on November 30th, 2016. And not long after that, there was another black hole collision detected by the LIGO instruments. The plan was that the Virgo instrument in Europe would start operating sometime in 2017. Before that, there was another black hole collision detected by LIGO. Virgo then joined on August 1st, 2017, and there was a period of that observing run, which lasted about a month, that was extremely productive, where in fact we're still analysing the data from that run. But quite quickly after Virgo joining, another black hole collision. And to give you, again, the key to these numbers, GW's gravitational wave, the number after that is simply the date. So 17 is 2017, 8 is August, and 14 is 14. So 14th of August, 2017, a black hole collision for the first time detected using 3 detectors, 3 observatories, and that's just a picture from the announcement, again, that was made in Italy, again to reflect this was the first time that the Virgo instruments had joined. And it was extremely important to have that additional instrument, to have the Virgo observatory operating for a number of reasons. To again talk you through these plots and what they're telling us. On the left here, what you see is really a projection of the sky, and marked on that, these large blobs that you see here are the areas of the sky that with the 2 LIGO instruments we were able to determine where a signal had come from. Because with a single gravitational wave interferometer, it's actually sensitive to signals from most of the sky. These are not like telescopes. They're not directional. We don't point our gravitational wave detector again. It's a very different way of sensing things. In many ways, it's more like a microphone. It has some sensitivity to signals coming, vibrations coming, again, from all over the sky, which in some ways is good to have that capability. But on the other hand, it means you don't know with one instrument where a signal came from. There is a antenna pattern. So there's some weak directional sensitivity, but not good directional sensitivity. And even with the 2 LIGO instruments, you can see, let's see, there's our first detection, 14th September 2015. There's really a large portion of the sky with those 2 instruments that we were able to say, well, the signal came from somewhere over there. And we do work with EM observing partners, of course, and did at that point. They were sent a trigger and requested to say, well, we think a signal came from somewhere in this portion of the sky. Could you possibly point your telescopes there and have a look? So this, of course, is much larger than a typical field of view than an electromagnetic telescope has. It's not efficient in any way to ask folks to try and look at this portion of the sky. And you can see there's the same was true for the other gravitational wave signals. Again, to give you the code, LVT was a smaller signal, not big enough for us to be confident to call it at that point a gravitational wave detection. That stands for LIGO Virgo trigger. Again, that happened, you can see, in October 2015. But it was consistent with a signal that looked like a binary black hole. Adding Virgo, that third instrument to this mix, gives us additional directional sensitivity, because with one instrument, we have weak sensitivity. With two, we can start to do timing, again, simply of when the signals arrived in the different instruments. So we triangulate back to where, that's where these blobs come from, to where a signal could have come from. The addition of Virgo, you can see, for this triple coincident event made an enormous difference. To have that third instrument widely separated from the others hugely enhanced our capability to do sky positioning, hugely narrowed down our uncertainty as to where that signal could have come from, and that makes a major difference, again, and as we'll see, turned out to be highly important, again, for the neutron star coalescence that was subsequently to come. So that network, that global network of detectors, is enormously important to have scientifically, and it was quite remarkable that so soon after Virgo turned on, it was able to make such a significant contribution to the science. So that's new capabilities, but there was also new science that could be done with the Virgo instrument there. Again, because it was widely separated from the other two, we were able to do new science in terms of looking at the polarization of gravitational waves. General relativity makes very specific predictions about how gravitational waves should distort space-time. And in fact, the little animation here shows you the prediction of general relativity. A gravitational wave then sort of traveling in a direction that's effectively down the middle of that tube there, GR predicts would distort space-time around it in this very characteristic way. And you can see the sort of distorting circle that I showed you earlier was effectively looking at the end point of this tube, the stretching in one direction and the compression of the other as this transverse gravitational wave goes through. Other theories of gravity make other predictions about how space-time should be distorted. This is the GR prediction. And with Virgo, we got additional information, additional spatial information that we're able to use to calculate the probability that the distortions really are of this form. General relativity, again, came out with flying colors, yet again, so that additional Virgo instrument also gave us the ability to do new science. And in terms of visualizing, again, what we have, there are different ways to do that. With, then, the detections that we have of binary black holes colliding, if we plot like this is simply the known black holes plotted in terms of their size, in terms of solar masses. Again, why was that first? Were all our you'll notice again, all our estimations of the performance of our instruments were in binary neutron star range. And in fact, for black holes, when we were searching for them to start with, we were not actually searching for black holes of this size, because previous X-ray studies, again, from electromagnetic X-ray studies, had suggested that the objects out there that caused matter around them to behave in such a way that suggested it was moving around a black hole, suggested black holes of about this size, up to, I think there's probably just a couple missing from here, up to about 20 solar masses or so. But the very first black holes detected by LIGO were about 29 and 36 solar masses combining to form a 60 solar mass black hole, and that was unexpected. And meant that, in fact, it was a great surprise to us, and we had not been looking for binary black holes of that size. Our search algorithms were not being tuned online at that point to do that. So those are from that first observing run. There's our second observing run with the LIGO, and then again one using the Virgo instruments. But there are different ways to visualize what this means. I pointed out right back at the beginning for that first detection that the properties of the objects are encoded in the signal shape. So you can see for the set of binary black hole collisions detected, here are sort of the best fit templates for those individual signals. That's the second signal, and third one with LIGO there. There's one with Virgo. And there's a couple of things to note. The first of which is that these all went through our detectors, well, these ones, in less than a second. And this one, the Boxing Day event, 26th of December 2015, however, lasted a bit longer. It's noticeably different. And if we go back to the previous slide, you'll see there it is there. That's telling us to some extent about the masses of the individual black holes that govern this. So if we plot those signals again, all we've done here is rescaled the time here, the time observable in our instruments. When something happened on the 17th of August, again with the Virgo instruments running, it looked remarkably different. This was clearly a different thing, persisting for considerably longer, a notably different source, again, that had turned up in our instruments. And that, again, that signal, again, is very characteristic of what's happening. You can see the persistence there is telling us these are smaller masses. In fact, this was the binary neutron star, the very first detection of a binary neutron star coalescence, publication from 20th October 2017. And again, with both the advanced LIGO and advanced Virgo instruments running, which again turned out to be exceedingly important, that 1 month run of Virgo was remarkable. This particular signal was seen in both the LIGO instruments, but not seen in Virgo. And that not being seen in Virgo actually was what allowed us to localize the source. Because I said each instrument has an antenna pattern. And there's sensitivity to most of the sky for gravitational waves with a single instrument. But there are directions, in particular for a gravitational wave that comes in at 45 degrees to the arms, in which there's no sensitivity because both arms are affected in the same way and they're set up to measure the differential motion of the masses. So not being seen in Virgo turned out to be exceedingly important. And that allowed the source to be localized to a sky region of about 28 square degrees. Again, very precise. Even more remarkably, it was also observed in the electromagnetic band because actually our interest, in fact, in the signal was triggered by the detection of a gamma ray burst by Fermi. This signal was originally seen in one of the instruments and triggered in, I think, the Hanford instrument in gravitational wave signals, but not in the Livingston instrument. And when we went and looked, it was there, but there actually had been another glitch. There'd been a glitch in the instrument during that time, which had meant that we would have automatically not particularly looked there. But it was possible to subtract that glitch and find the binary neutron star signal in both of the instruments there quite clearly. Within 1.7 seconds, again, the gravitational waves arise first, a gamma ray burst detected by Fermi 1.7 seconds later, and together that triggered an observing campaign that was really quite remarkable. So there, again, is that characteristic gravitational wave signal, the sweep, the increase in amplitude and frequency with time. Plotted above that, again on the same time scale, our data, I think, from Fermi there with the gamma ray burst signal arriving 1.7 seconds later. Remarkable to us was the fact that we could localize with the 3 gravitational wave signals the source of that to a portion of the sky that actually was better than could be done with the gamma ray burst. And I think that was not something we had particularly expected, but there they are, sort of with that overlapping patch in the sky. And not long afterwards, an optical signal was also detected from there, along with what turned out to be a really, as it says here, an unprecedented set of observations using both electromagnetic and gravitational wave observatories. This beautiful artist's impression here of perhaps what happened. So on August 17th, the gravitational wave signal came in, 1241.04 UTC. Within 2 seconds, the gamma ray burst was detected. After several hours, there was a bright optical source which started off in the blue and then rapidly faded, again with a beautiful set of light curves coming, showing the the optical signals from that. Then infrared, UV, X-ray, radio still being observed again, and I think it's the first time there's been this pre-observation and continuous observation of an event like this. And it really has produced, again, a quite remarkable set of rich science, putting together the gravitational wave signals and the electromagnetic observations. And this is a list of some of those. Even this list is not comprehensive, and I won't talk about actually all of these in any detail. Confirmation of neutron star mergers as a cause for short gamma ray bursts. The first confirmation of that, the gravitational wave signal showing the in-spiral of the binary neutron stars before they merged, and then the subsequent observation of the short hard gamma ray bursts. Remarkable information on the speed of gravitational waves compared with the speed of light. So there's 1.7 seconds between the gravitational wave and the electromagnetic, the gamma ray burst signal arriving. The distance to this source, which I think I skipped over there, was actually 40 megaparsecs, the closest gravitational wave signal a source yet detected, and actually quite close. I think it's 130 million light years. So the difference in the arrival times was 1.7 seconds in about 130 million years of travel time. So, which allows a quite remarkable, again, confirmation with that 1.7 seconds probably being real, probably being part of the emission process that took time for the gamma rays to be produced. That amount of time that this particular source spent in our observation band gives us additional capabilities in being able to test GR because the signal persisted for so long. So additional ability to test GR in extreme gravity. Because this time, again, we got electromagnetic signals this time because there was real matter there. These real neutron stars. When the neutron stars merge, how they merge, the exact signal that they produce, starts to give us information about the equation of state from neutron stars and nuclear astrophysics. Again, about what the condition of matter is. Again, and so there are publications around each of these individual extracted physics that can be done. Again, and in some of these cases, and I'll talk more about that, we are clearly just at the start. There's just one source, one observation that starts to give us information in each of these areas. But we really are just at the start of what we can do. And a particular example of that is this one here. And again, I'll show you one result from this. An independent measure of the expansion rate of the universe from gravitational signals, a gravitational probe. Because the gravitational wave signal has embedded in it the absolute distance to the source, and that drops out of the gravitational wave signal. And this particular source we had a host galaxy for, so could work out redshift. We're able to get a gravitationally based measure of the Hubble constant. It was very exciting. And then another piece of fantastic science that came out of this individual event was around the synthesis of heavy elements. And this is, again, not my area of expertise. It was compiled by colleagues in the astronomy community. But those light curves, the observation of the behavior of the emission from this particular source observed electromagnetically, allowed deduction of the heavy elements that were being produced there. So the periodic table now looks like this, with many of these heavy elements ascribed to being formed in the merging of neutron stars. And again, it's the combination of the gravitational wave information and the electromagnetic information that has allowed that deduction to be made. This is one that particularly caught, I think, the imagination, particularly, of course, the existence of gold and platinum there when this announcement was made. So of the many places that this got reported, one that particularly amused me was the front page of the Financial Times. I can only assume it was the gold produced in those merging neutron stars that they felt would be of particular interest to their readership. but it was quite nice to see that we made a spectrum of the press on that particular announcement. As the other result, again, I wanted to pick out was the Hubble constant result, because I think it's particularly interesting. It's exciting to be able to do this. So this plot shows values of the Hubble constant, the sort of confidence, the probability of those being the right value. And there's measurements in green, I think, from Planck, in red, I think, are the supernova results. And at the moment, of course, what's interesting is those two different collaborations come up with two slightly different values for the Hubble constant, measured again using electromagnetic techniques. In blue, you can see our gravitational wave result. The error bar is large because we have only one observation at this point. But what's exciting is that is an independent measurement. It does not have the same systematics that come from the electromagnetic studies. It does not, you'll see, allow us to differentiate yet between those two results. But this is a case where it really is first steps. Again, and it's a close source. What we obviously want to do is not only measure more of these kinds of events, but from further distances out in the universe. So we're really just at the start of this kind of measurement. But from this one observation, the science that we were able to produce was rich and quite exciting. So we're starting now to fill in a plot of our knowledge of the endpoints of stars that looks a bit like this, with these known neutron stars. There's our first observation of merging neutron stars to an endpoint that was probably a black hole. Our electromagnetic observations giving us information about black holes, complemented by the gravitational wave observations, extending this family tree of the endpoints of stars that itself starts to feed into information both about processes in stellar astrophysics that can produce black holes of the size that we see, and creeping up, again, in terms of masses of known black holes that there are out there, contributing to our picture of what's happening in the evolution of our universe and galaxy formation, with a very interesting gap appearing there. So what's coming next? Well, in the next few years, it's actually getting LIGO and Virgo to design sensitivity. All the science has been delivered with the instruments not yet at design sensitivity. There's still a factor of several away from that. So there are various scenarios for how that might go, but over the next few years, you can see we're in the gap here between the second and, at the end of this year, probably the third observing run using the LIGO instruments. And these, again, will be binary neutron star ranges, again, with a commissioning period, a significant commissioning period, with the aim of improving the sensitivity of the LIGO detectors, further working towards design sensitivity. Virgo, again, is also in a commissioning period, again, with the idea of doing a joint run. And the next instrument to come online, we hope, will be CAGRA. So these, as we go out, these numbers become more tentative in terms of timing, with CAGRA joining, again, to give a fourth observatory in that picture. And why is that still important? Well, in terms of directional sensitivity, we have done much better by adding the Virgo instrument. And again, just a reminder here that it's the triangulation, the arrival times between the different detectors that allows us to work backwards to where a source may have come from in the sky. Here is what even with the two Hanford instruments, the Livingston instrument and the Virgo instrument, here's what our estimated uncertainty is, depending on where a source is located in the sky. So you can see for some portions of the sky, actually our uncertainty would be pretty small. A source located there, we would be able to pinpoint quite well. But there are some portions of the sky for which we still have these large blobs of uncertainty. We would not be able to say with confidence, even with the Virgo instrument running, where a source had come from. And those red X's actually are positions in the sky that we really wouldn't have significant sensitivity to. Adding the instrument in Japan and an instrument in India makes a huge difference. there's still significant scientific drivers to complete that advanced detector network and have the instrument in Japan and the instrument in India running again. So there is a real driver to have that advanced detector network. So around 2020 or so, we would hope to have a detector network that looked like this just being the baselines in between the individual observatories. So the globe is plotted here, so there's the two instruments in the US, we have Virgo in Europe, India and Japan. But you'll see it's quite striking in looking at this globe that these are all still in the northern hemisphere. There's a gap in the southern hemisphere. And when you do this much more scientifically and you either start with the detectors we have, or in fact, if you start with a clean sheet of paper and say, where would I optimally want to position an instruments to best do sky location, it turns out Australia is the obvious candidate for where you would want to put another instrument. And we have colleagues in Australia, there's a very strong gravitational wave effort there. And so looking to the future, again, that is an as yet unfulfilled opportunity that scientifically certainly would add to the capabilities of gravitational wave astronomy. So beginning the instruments to design sensitivity, completing the advanced detector network, again with India and Japan, what comes after that, and actually hopefully in the not too different future? You'll remember it took us a long time, again with precision instrumentation, to get to the point that we're at. We have these fabulous infrastructures. We are not yet limited by the capabilities of the infrastructures themselves. And taking a bit of a look at the timing, going back to the early 2000s when these instruments were first conceived and sort of funded, it's been more than 20 years actually for the Virgo infrastructure and actually longer for LIGO and GEO since these infrastructures were first put in place. These are, and by infrastructure I literally mean these are huge civil engineering efforts, 4-kilometre long vacuum pipes in the case of LIGO, about over a metre across. All of that infrastructure has been there for quite some time, and in that infrastructure, of course, we first did initial runs with the initial versions of these, set upper limits, improved those a bit, went to the advanced detector stage with, of course, that first detection coming in the 2015 range, but we are not yet at the final capabilities of these infrastructures. The instrumentation inside them isn't yet physics limited by the physical infrastructures that they're in. So there is a possibility to do more in those infrastructures before we get to the point where we might want to take another leap in what we can do. So actually, since before that first detection, since in 2015, actually stimulated by the NSF in the US, the community has got together and has been working to consider what more could we do? What would the capabilities be still with the infrastructures that we have? And there have been a series of meetings on that. And this plot here, there's frequency along here. It's really a spectral plot of noise. Up the side here, you'll see strain effectively sort of telling us about delta L over L and what the noise limits to the performance of the instruments are at different frequencies. And so we've looked at that, considering what the different sources might be, what the payoffs in science would be in pushing down, and the technical readiness, and of course, costs. And again, these are public documents, so you can have a look at those in terms of what looks doable. Our black hole sources are coming in at low frequency here. At low frequencies, what bothers us? Well, with our mirrors and the instruments, actually at low frequencies, there's a number of sources, one of which is Newtonian noise, straight gravity gradients. So this time, our mirrors are hanging there, suspended in space, and instead of a gravitational wave coming from far away moving them, as the Earth moves, straight seismic motion of the Earth, not actually shaking the mirror by physically vibrating it connected to the Earth, but actually the straight gravitational pull from the Earth moving actually can pull the mirrors. So, and that happens at low frequency, and there's a steep sort of frequency rise. At higher frequencies, it's associated with the laser. Again, counting statistics in the detecting the intensity at the output of the interferometer. And in the mid-band, it's thermal noise. And in particular, thermal noise, Brownian motion of the optical coatings that we put on the front of those big glass masses to make them into mirrors, along with, again, that Newtonian noise at low frequency, the Brownian thermal noise of those suspensions again. But those are things that we think, again, in the laboratory, we have ways to tackle to get sensitivity gains of about 5 in event rate over the baseline design of the instruments. And why is that worthwhile? If we look at this plot here, this is sort of expected number of colliding black holes per month of coincident time. So coincident time means you have to have 2 detectors running, both operating in science mode, so that you can be confident you've made a detection. And so there's our first observing run, 01, back in September 2015, and that's kind of the sort of median black hole coalescence rate with some 90% confidence limits on either side. And there's our 1 and a bit. Remember, there was that LVT trigger, 2 and a bit, that's 2 and a bit detections in 01. Here's 02. Again, I think we published 3 black hole coalescences and, of course, a binary neutron star. But we're still analysing the data from 02. And when I think our O2 sensitivity is not quite as good as we had hoped in terms of this plot here. So in truth, this should probably be slightly lower. So again, we're in that 90% confidence band. We're on track again for this plot. There's advanced LIGO design sensitivity. And again, this is per month of coincident time. So we're at roughly sort of tens of events per month. With slight improvements of the type that I talked about to upgrade the advanced detectors, we're into the hundreds per month range. It's a major difference and quite remarkable, again, considering where we were just a couple of years ago, to think that within a few years we could be at that point. So there's strong motivation because we get, as we improve the sensitivity, the cube of that in terms of sources that we can detect to maximize what we can do. This is, of course, for binary black holes. We clearly want also more binary neutron stars, and it would be really nice to see a neutron star black hole merger, but the rates there, of course, are more uncertain. We will then, looking to the future, at some point hit the limits of the infrastructures themselves. There's that band of Newtonian noise. Eventually, we may want to make the instruments bigger. Remember, not only are they not tabletop, the bigger you make them, the more sensitive they are. These were 4 kilometers because that was a sensible break point at the time in terms for the LIGO instruments of what we felt could be done, but there are visions now for larger instruments, 10 kilometers or even longer. And there are a set of challenges that would challenge the infrastructures that are there if we want to cool the test masses to reduce the thermal noise and make them cryogenic. If we want to make the beam bigger, again, we already have a sort of 32 centimeter test mass. If we want to make the test masses bigger, make the beam bigger, average that thermal noise away, that can challenge the limits of the infrastructure. So there's a whole set of these, again, that may push us to see what that really we would need a new infrastructure. This is not a new thought. In fact, that what next question has been thought about since the time when we were building the advanced detectors back in the 2000s. And in 2005, the European Science Foundation supported a workshop to ask, the communities to get together and look to the future. Out of that came a design study funded under FP7, bringing together the groups in Europe. At that point, again, France, Germany, Italy, the Netherlands and the UK being the founding countries, but with other countries joining since then, that produced a very nice design study, a conceptual design for what a new infrastructure in Europe might look like. That has been carried forward in a number of roadmaps, sort of visions for where the field might go. And I think the latest of those was actually launched just this week in Brussels, earlier this week, in fact, on Tuesday. And in what's called the APEC roadmap, which is the strategy sort of conceived by the European agencies with the community for how astroparticle physics in Europe might look, again, over the next 2017 to 2026, which contains, not just for gravitational waves, but for the whole, all fields and particle astrophysics, recommendations for where Europe might want to go to position itself in the global stage. That was a very interesting meeting, and it was a very positive meeting. There were talks from Jan Robert Schmitz, DG Research and Innovation and the European Commission, and actually also from Franz Cordova, came across, the Director of the National Science Foundation. And in thinking about going forward and about the future, it was very interesting to kind of hear the messages that were coming forward in their talks. From the European side, there were talks about, for the next programme, about opening further the European programmes to that international linkages, to thinking about strategically how to do that. From the US side, again, France talked about the need to strengthen international coordination for large infrastructures, for planning, for review, and for support, again, at that international level. And so it was interesting to hear those messages. I have to say it was also interesting to hear from Jan Robert Schmitz the messages about budgets in Europe, that discussions had been positive about science. They're thinking about the future, again, nowhere near anything being decided yet, but there was real recognition of the importance of science across Europe. So buried in there are recommendations about ET, about the gravitational waves field in Europe, and again about how that might go forward. But it was an interesting meeting, talking and hearing, again, perspectives about strategy for science going forward. And it really is, we've talked about ET. ET is probably the furthest ahead by far in terms of concept for a new infrastructure. But it's a global picture, a global field. You can see that from the need for an advanced global network. Single countries are not the way the field works or is going. And so there are also discussions, again, in the US about how in the US concepts are being put together for a new type infrastructure there, and how that might fit into the global picture in the future, going from our advanced detectors, maximizing the use of the infrastructure, again, to new infrastructures at some point in the next decades. Of course, simultaneously, the technology for those is being developed, again globally in labs here in the UK, in Europe, around the world. Perhaps even bigger instruments. 10 kilometres was the vision for ET, maybe even bigger. Perhaps putting it underground, as in fact CAGRA will be, to mitigate the effects of Newtonian noise from seismic vibrations. Instead of a 200-watt laser, do we need even higher laser powers to beat down that noise at high frequency? If we want to cool to cryogenic temperatures, no longer using glass or fused silica optics, but switching to sapphire, that's actually a sapphire optic, which disappointingly just looks like a big piece of glass, I have to say, but it's twice as dense, roughly, so if you try and pick it up, you quickly realize it's not fused silica. Potentially using crystalline sapphire optics or silicon optics, again, which conveniently comes in large pieces, but inconveniently is not transmissive at 1064 nanometers, so that may require a switch of wavelength, again, producing high-power lasers at 1550 nanometers, where silicon is transmissive. A whole bunch of different technical options that, of course, need to be science-driven. Where is the science going to drive us in terms of the future capabilities that we wish to have? Well, our field, because it's an international field, because it's diverse, and because the challenges are large, has always been relatively good at being focused and organized on an international scale. And so there's a body that exists called GWIC, which stands for the Gravitational Wave International Committee. And that's a formal grouping of laboratory directors and leaders in the gravitational waves field. It's actually a working group of EUPAP, the International Union of Pure and Applied Physics. So it's formal status, but it brings together leaders of the international projects with a mission to help coordinate and support the field of gravitational waves going forward, and that's gravitational waves broadly. I've talked a lot about the ground-based detectors, but we also, again, have visions for space-based detectors. There's pulsar timing, again, and we're just at the start of a set of new capabilities in this field, so representatives there are also included. And actually, back in 2009, this body worked with the community, with our funders, with adjacent fields to put together a roadmap for our vision. And what I've talked about today, actually, to a large extent, is embodied in that roadmap, our vision sort of going forward for how the field might want to go, the need for that advanced detector network, for detector upgrades, eventually for new infrastructures. So, given the recent detections, we're at a very special time, again, with new information, new thoughts about the science that can be done, and the coordination that we need to do with our colleagues in electromagnetic and astroparticle communities. So GWIC, again, I'm the current chair, has put together a subcommittee specifically to look at this, covering international and diverse perspectives, looking at, again, ensuring we're doing the best in terms of coordinating the community. There's a particular subgroup, and again, this is an open exercise, an open call. Anyone who's interested in the science is very welcome to join. We've many members from the astronomy community outside of gravitational waves working together to work on the science case, the science drivers, and articulate that for the gravitational waves field going forward. And think in this international world how we best work together with international facilities, perhaps in a new way than we've done before. There's a link to the website there. Again, if you want more information, please feel free to get in touch with me, but that's ongoing. Because we really are only currently probing a fraction of the capabilities of gravitational waves. We expect gravitational waves to be produced by sources over this enormous spectrum of frequencies, and again with a diverse range of sources, which just as in electromagnetic astronomy, need a diverse range of instruments and capabilities to detect and study them. And everything so far I've talked about is actually just up the right-hand side here, the ground-based detectors. There are some very exciting sources in science for which we will not be able to detect them on the ground. Again, that low-frequency gravitational gradients at some frequency will eventually hit us, and we will need to put detectors in space. So I'll just finish by saying a few words about that. This is a picture actually now from 22 years ago, which rather pains me to think about it because I am actually in it. And many things apparently have changed in 22 years, but not my haircut. I was also somewhat appalled to discover. This is from 22 years ago, and it's taken at Rutherford Appleton Labs. It was the first LISA symposium, Laser Interferometer Space Antenna. And you'll see I'm there, and there's a significant overlap in interests in the science, of course, between people on the ground. That's Jim Huff, who many of you will know, Kirsten Dantzman, Harry Ward, and interested in what science can be done with a detector in space. Now, even although that was 22 years ago, it is, of course, not the start. Even before that, again, there were significant discussions pre-1983 about what a space mission for gravitational waves might look like, again, coming partly from colleagues in Boulder in the US. And over the years, again, if it takes a long time with ground-based instruments, it takes even longer with space missions. That mission has evolved in terms of the vision for what such a space mission might look like. But around 1997, the need for a technology pathfinder mission was defined, again, to test out some of the necessary technologies that would need to be flown in such a gravitational wave detector in space. And LISA Pathfinder then was a single spacecraft mission. You can see here the concept for a space mission. It's a similar principle to on the ground. We have widely separated, in this case, spacecraft on the ground. It was our mirrors with laser sensing between these spacecraft so that a gravitational wave passing through, in this case, changes the separation between the spacecraft, and that's the effect that's sensed. There's a lot more room in space, and so instead of a few kilometers long, again, the baseline for this has been several million, in this case 5 million kilometers long in the middle there, large instruments. So for Pathfinder, some of those thoughts and that technology was shrunk down into about 30 centimeters, flown in a single spacecraft to test out some of the sensing. That also happened over the last couple of years and was exceedingly successful. The Pathfinder mission more than met its requirements and demonstrated that the flight of this technology, again, it was highly successful and very appropriate to consider the future of a space mission. So I think currently ESA have, as one of their large class launches, an L3 launch in 2034 or maybe earlier, penciled in, or more than penciled in, it's in their forward look as a mission in space. And it really is opening up new capabilities, new thoughts about what science can be done. This is a nice paper from my colleagues in Birmingham, talking about prospects for multi-band gravitational wave astronomy, pointing out that with advanced LIGO and Virgo, what we are seeing are remember it flashed through in a fraction of a second, the final last few cycles of black holes orbiting one another before they collided. LISA, potentially, or a space mission like LISA, could detect actually the early stages of those black hole, stellar mass black hole binaries circling round one another, years before they coalesced in the band of the ground-based instruments, giving point-forward information to the ground-based field so that a future ground-based instrument, probably beyond the advanced detectors, probably in the Einstein telescope area, would know, again, when and where to look for coalescing black holes, a whole fantastic set of new science, of which this is just one example that can potentially be done. So the ground, the space, there's pulsar timing, and of course cosmic microwave background experiments to give us additional information still to look forward to. So to finish, it's been a fantastic few years. The detection, again rewarded by the Nobel Prize, was a wonderful achievement, but it's mainly the beginning that we're at of a new era in how to study the universe, bringing together, and I think that's clear, gravitational wave signals and our electromagnetic and particle astrophysics facilities and future generations of those to add to this techniques that we have to study our universe, and I am very confident there'll be more exciting discoveries to come. And I will stop there.
Thank you very much. That was a fascinating talk and a wonderful start to our day. I'm sure there must be questions. There's a fancy device, which apparently you can throw.
This may be a naive question, but what is the implication of these new instruments for getting a much, much better value of the old-fashioned Newtonian gravitational constant?
Of big G?
Big G.
So oh gosh, that's a very good question. I'm not sure that we contribute significantly to that. I mean, big G is a fascinating subject all on its own, and many of my colleagues in the precision measurement community, there's sort of overlap in their instrumental interests between what we do and what they do. In fact, you probably know I don't know if you know Jim Fowler, again from Boulder, is actually a visiting professor with us in Glasgow, and he has spent part of his life measuring big G in the precision instrument world. So we work closely with him actually in discussions around the technology, and because the suspensions and that precision technology is very relevant, that hunting down of systematic noise sources. But I'm not sure that our instruments themselves are improving knowledge around big G. We feel they are our cousins in terms of precision measurement.
Henning, up there.
You mentioned that it might be possible to also observe the early stages of these mergers. Does this mean that in principle one could also think about detecting things like planetary motion in kind of stars that are nearer to us, or is this completely out of the question?
I think that you really need, so for planetary motion, I think the signals are simply, well, for very close things like the moon, that we get the gravitational tides, but those are not gravitational waves. the gravitational waves from planetary motion, I think, are just too small. Still, if you think about the objects we're talking about, it's neutron stars and black holes, and we simply need that super strong gravity to get us gravitational wave signals big enough for us to detect true gravitational wave signals.
Chris.
Sheila, it's clear that the detections you've made have revealed black holes of masses and sizes that were perhaps unexpected. So my question was, would you, why have we not had traces of 50 solar mass black holes coalescing through electromagnetic signatures before? And why does the population of GRBs, of which there are plenty, why haven't they led to more detections with LIGO?
So I'll answer, well, the second one first. The
Okay.
GRB, so one thing I didn't mention about this is it's an unusual GRB. It's weak. And in fact, there are different models. Again, I don't know if I have that slide here. There are different sort of models, I think perhaps. There are different potential models for what that GRB looked like, what actually happened there, because it was weak, it was probably off-axis, and one of the speculations has been that perhaps there is a larger population of these things that haven't been studied because you tend to study the strong signals that come in. So I think also in terms of rates, still, if you look, this also was particularly close.
Yes.
It was very close. If you look at the rates, we still, for binary neutron star coalescences, we've still detected one. It's still not clear. I mean, that is still, of course, with one consistent with the rates that we had before, which suggested at design sensitivity, we might see several a year or so. So we're not at design sensitivity yet. So I think there's no inconsistency in terms of the rates yet. The GRB part of it, though, is very interesting in terms of it being potentially weak off-axis, and that has opened up a lot of interesting questions in the GRB world to go back and think about weak GRB sources. And the other one in terms of the black hole size, it's a good question. I don't know I think we just don't know. So for each of the binary black hole coalescences, we have sent out triggers, the electromagnetic colleagues have looked and haven't seen an electromagnetic signal of any particular kind that was statistically significant. I think there was perhaps in at least one of those a potential weak signal, but it wasn't statistically something anyone was willing to really go with. If the black holes have been there for a long time and have essentially cleaned out the area around them, there simply may be no significant matter to produce an electromagnetic signal. They are big, and they're big at the point that's interesting in terms of having implications for the stellar conditions for the star that must have produced them. But I don't think they don't break any rules of physics there yet. They just have significant implications about the metallicity of the conditions of the stars that produced them. So it's interesting. I don't think they're forbidden, but they are in an interesting space.
Okay, thanks.
How close are you to detecting a single gravitational photon?
A graviton. So I think we're still far away. When you look at the energies of the individual gravitons, it's not something we will be sensitive to. We are only sensitive to the wave portions of those. What we can do is set a limit on the mass of the graviton. In fact, from these results, it's one of the results I didn't put up, which is exceedingly tight from the observations that were made. So we can set a limit on the mass of the graviton, but we won't be detecting individual gravitons. It's just not energetically possible, I think, using these instruments.
Perhaps I could just follow up on that. GR is a long-established classical theory, and you mentioned possibilities beyond GR. How sensitive are you to physical models which extend GR, and what are the runners and riders in the race?
So again, not my speciality. What I think I can say is that, again, from this observation of the binary neutron star coalescence, the observations there actually ruled out some classes of MOND, which made predictions which were inconsistent with the observations that were made. So that's very interesting. In terms of what's left, at the moment we are working hard on testing GR, but I'm not going to give you my favourite non-GR theory. But I think what I do find very interesting is, as we make detectors more sensitive, we will be more sensitive to the details of black hole mergers. And I think that is a particularly interesting area. Now, it may be that physics is such that GR just won't break, that it's, the universe is good at hiding from us things that we just shouldn't look at. But I think that's the area which I'm particularly interested to see as we go forward with more sensitive detectors and get more precise measurements of what happens in that collision of black holes and the event horizon mergers.
Okay, thank you. Any more questions? So, oh, yes, there is.
At the moment, you've just got that quite broad measurement of the Hubble constant to match the two that don't quite agree. Do you have an estimate for how long it might be before you have something that might distinguish between the two or give a kind of precision?
It's a good question. Again, I don't know I could find the answer to that for you, but I don't know it off the top of my head. You can see that was just one. And what we need for these are, again, to know the host galaxies. And so, and in fact, I know my colleagues are working very hard on this, on understanding where we are. There are gaps in galaxy catalogues, even when you start to look at this. The numbers exist. I can get them for you offline in terms of at design sensitivity, how well we think we could do in terms of percent, accuracy on the Hubble constant. It's not, I think it's much better than is there, but it's still probably not as good as our electromagnetic colleagues think that they will be able to do on that same time scale. What's interesting is that this is such a different way to do it with a gravitational probe. So as they improve their accuracy and we improve ours, to see how this pans out in terms of those numbers is where I think it's going to be interesting, but I can certainly get the numbers for you offline.
So I think that's probably a good moment to break for coffee. I'm sure Sheila will be happy to talk to anyone in more detail there. And please come back promptly for the 11 o'clock session. And don't forget the panel discussion as well after lunch. Thank you very much.